Good morning, one and all present here. Today we have our speaker, Dr. Srilata Chebrolu, currently working as Assistant Professor in National Institute of Technology, Andhra Pradesh. Dr. Srilata obtained her PhD from NIT Warangal. She is an expertise in machine learning, soft computing, big data analytics, pattern recognition, artificial intelligence, data science, and data mining. To list few of her achievements, Dr. Srilata received PCS Research Fellowship under Research Scholar Program while pursuing her PhD. Also received MHRD UGC Fellowship while pursuing MTech in Andhra University. Madam has conducted 1 week faculty development program on soft computing techniques for analysis of large-scale data sets, sponsored by ICT Academy, NIT Warangal. Also delivered lecture on machine learning algorithms at AICT-sponsored FDP titled Emerging Trends in Machine Learning for Biomedical Applications in Narasaraopet College of Engineering. Madam is also a reviewer in International Journal of Geographical Information Science, Taylor and Francis Group. She is certified educator, Microsoft certified educator. And Madam has published more than 10 research papers in reputed journals and conferences. May I now request Madam to handle the session.
Yeah, thank you, sir. Thank you for the introduction. Yeah, so let me share my screen. Today I am here to present reinforcement learning. Can you see my screen? You can see my screen, right?
Yes, ma'am, visible, ma'am.
Yeah. So today's topic given to me is reinforcement learning. Okay. Under this reinforcement learning, reference that I have taken is machine learning by Tom Mitchell. Okay. This is the reference that I have taken. And the topics to be covered are introduction to reinforcement learning, the learning task, and then Q learning. In Q learning, we have Q function, Q learning algorithm, an example, illustration example, and the convergence of this algorithm, and then non-deterministic rewards and actions, and temporal difference learning. These are the topics that we have to cover for today. And then introduction. Reinforcement learning, it addresses the question of how an autonomous agent, how an autonomous agent that senses and acts in its environment, can learn to choose optimal actions to achieve its goals. So let me introduce an example where reinforcement learning is applied. Okay, so here we are saying that controlling a mobile robot, right? So there will be a set of states in which a robot will be working. Okay, so let me show you this. Okay, this is the environment. Okay, this is the environment. Agent is a robot. Okay, in our example, agent is a robot. Okay.
Excuse me, Professor. Sorry to interrupt. Can you please go for a full screen mode slideshow?
Yeah.
Thank you. Thank you.
Yeah. So agent is the robot, and this agent will be working in this environment. Okay. This will be working in this environment, and the agent has to move from one state to another state. It has to transition from one state to another state. And what will be the initial state? Initial state can be any one of the states. Okay, initial state can be any one of the state among the set of states, and there will be a set of actions, and this agent or robo, for example, that will be transition from one state to another state, and by taking some action, okay, by taking some action, and then it will be giving some reward. Okay, there will be some reward. A reward can be a positive reward, it can be a negative reward, or it can be a zero reward. Okay, let us see this. So initial state in this case is S naught. Okay, initial state is S naught, and now the agent has taken action A naught. Okay, agent has taken action A naught, and it has moved to the state S1. Okay, and it has got the reward R naught. Okay, on moving to the state S1, it has got the reward R naught. Like that, it will be working in this environment infinitely. Okay, so let us see one more example. Let me show you another example. Okay, yeah. So simple grid world environment. These are the states. We have got 6 states. Okay, here we have got a 6 state, and G is the goal states. Here G stands for the goal state, and here states are 6. Okay, and then see the rewards. Rewards. These zeros are all there, right? Zeros. 100 is here, and here also we have 100, right? So all these are the rewards. Okay, and the arrows, they indicate the actions. Okay, move up, move down, move right, move left. These are arrows indicate an action. Okay, saying that this arrow indicate that we have to move to right direction, move the right direction. On moving to right direction from state S1, let us say this is state S1. Okay, on moving to right direction, let us say we have moved to state S2. Okay, na? And then the action that we have taken is move right. Okay, na? Move right. And then what is the reward? Reward that we have got, or the agent in our example robo, that it has got a reward of 0. Okay, na? It has got a reward of 0. Okay, and then here, if you see here from this state, if it is going to the final state, that is the goal state, goal state is also called as the observable state. Okay, because this is the final state, and then on making any more actions on this state, it will still remain in that state itself, because it's the final state. Okay, so and then see the reward. It is saying that from this state, if you move to this goal state, agent will get a reward of 100. This also, here also it indicates 100. Okay, so this is the environment in which the agent works. Okay, now let us go back to the definition. Okay, let us see the definition. Okay, reinforcement learning addresses the question of how an autonomous agent, okay, how an autonomous agent, autonomous in the sense it will be working by its own. That's why it is called autonomous. Okay, and then that senses and acts. It is taking some actions, and what is meant by senses is there will be some sensors attached to this agent. Okay, na? Sensors attached to this agent, so that's why it is called sensing and acts in its environment. We have already seen, right? It's the states in which this agent has to make a move. Okay, can learn to choose the optimal actions to achieve its goal. Okay, optimal actions in the sense it has to go to the final state. Goals can be many. Okay, let us say if you take the same example, when the charging is low for this robo, then it has to dock to the plug point. That is the goal. That might be the goal. Or when a printout has come, this robo has to go there and get the printout. Okay, that might be another goal. So optimal actions in the sense, let us say if we let me go to the figure ones example. Yeah, So if you see this example, let us say we are in this state. We are in this state. And if it has to go to the final state or the goal state, then what is the optimal path is to make a move on a top move. It has to make a top move, right? Yeah, let us say that is called the optimal. Okay, now optimal action at this point of state is to make a move, up move. Okay, so that's why in the definition we have this optimal action. Okay, so to choose optimal actions to achieve its goal. Okay, so if we once again see the definition, reinforcement learning addresses the question of how it's also a learning algorithm. Okay, it's a learning algorithm. We will see how it learns. Okay, the question of how an autonomous agent that senses and acts in its environment can learn to choose optimal actions to achieve its goal. Okay, if you have any questions, you can raise your voice. Okay, and then RL tasks such as learning. Okay, so what are the examples? It is control a mobile robot, or learning to optimize operations in factories. Operations in the factories, in the sense there will be products that will be produced in the factories, right? Products that will be produced in the factories, and optimization is we have to increase the productivity, maximize the productivity, provided the cost of producing the products has to be minimal, has to be at minimal. Okay, that can be an optimization operation in the context of factories. Okay, and learning to play board games. Okay, so board games there can be many games, right? Board games, right? So backgammon is one game where RL has achieved some world class performance. We will see that also. Okay, so RL can be used in these applications. Okay, next. So terminology here is we have to know what is an agent, environment, action, state, reward. Reward can be positive reward, it can be plus 100, or it can be minus 100. Let us say a fire pit is there. Okay, and the rover has made a move to that fire pit. Okay, in that case it will get a negative reward. Okay, na? In that case it will get a negative reward. And when it went to some state where some other resources are there, then it may get some positive reward, if not the final state. Okay, and zero reward, it may also get a zero reward. And penalty and all we will see. Control strategy or policy in the sense the policy that has to be optimal policy has to be the optimal policy. So it is the sequence of actions. Policy is the optimal sequence of actions that has to be made by the agent to move, in order to move to the goal state. Okay, goals and all we have already seen, right? So these are the terms that will be used in this. Okay, so reward or penalty. Okay, so a negative reward can also be called as a penalty. Okay, so each time the agent performs an action in its environment, okay, a trainer may provide a reward or penalty to indicate the desirability of the resulting state. We have already seen that, right? So when it moves from one state to another state, it will get on a particular action. Okay, on a particular action, it may get a one reward. If it makes a top move, it will get a some reward. And if it makes a left move, the reward may be different. Rewards are different on each action. Okay, so it can be called as a reward or a penalty. Okay, for example, when training an agent to play a game, the trainer might provide a positive reward when the game is won, negative reward when it is lost. Okay, na? Negative reward when it is lost, and zero reward in all other states. Okay, when it is won, one state on reaching the win state, it will get the agent will get a positive reward, and on reaching the lose state, it will get a negative reward, and rest all states will be there, right? They are all given as a zero reward in the in an example of a board game. Okay, and a task of the agent is to learn from this, the policy. Okay, na? The policy or the control strategy. We are talking about control strategy, right? Policy or the sequence of actions. Okay, all are the same. Or the sequence of action. The task. Okay, the task of the agent is to learn from this indirect delayed reward. Why it is called delayed reward is in the sequence of transitions from one state to another state, it will be getting some rewards, right? It will be getting some rewards. Okay, to choose sequence of action that produce the greatest cumulative reward. If we sum up all those rewards, okay, if we take the cumulation of all the rewards, then we have to choose the policy or the sequence of actions that are generating the maximum reward. Okay, that is the objective. That is the objective. Okay, so objective of this reinforcement learning. Okay, objective of reinforcement learning is to come up with an optimal policy. Policy, by policy we mean a sequence of actions the agent has to take. Okay, na? In the environment. Okay, so Q learning. Q learning is an algorithm called Q learning can acquire optimal control strategies for delayed rewards even when the agent has no prior knowledge. The agent does not have any knowledge, okay, of the effects of its action on the environment. Okay, see, the agent doesn't know what reward it is going to get by taking some action when it is in some state. Okay, so that's why it is called no prior knowledge. Okay, rewards and all. Okay, let us say 100 reward or 0 reward or minus 50 reward. So all these things the agent doesn't know. So that's why it is called no prior knowledge, okay, of the effects of its action on the environment. So it is Q learning. It's an algorithm that will acquire this optimal control strategies. Okay, next. So robot example. Now we are considering the example of a robot. It is or the agent. It has a set of sensors. Okay, na? The set of sensors it can view. Okay, it can observe the environment. Okay, the set of sensors will be the cameras. Can be the cameras, forward camera, backward camera, and all. Okay, so through which it will be sensing the environment. Okay, and it will be having a set of actions to perform. Okay, na? So that it will move from one state to another state. Okay, cameras. So these sensors can be cameras, sonars, and actions like move forward, turn, move backward, move right, move left. All these can be the actions. Okay, so its task is to learn control strategy. So that is a policy. Okay, for choosing actions that achieve its goals. It can be anything. Goals can be anything. Like for example, the goal of docking into its battery charger. When the battery is low, then it has to automatically go and dock itself into the battery charger. Okay, that is the goal when the battery is low. Okay, so the robot might be having so many goals, and it has to undergo some learning without any prior knowledge. It has to learn in this infinite. It has to learn infinitely in this environment, and then it has to come up with an optimal policy. Optimal policy for achieving its goals. Goals can be many. Okay, so see here. So objective of RL. Objective of RL. What is the objective of reinforcement? RL, reinforcement learning. Okay, so its objectives are how such agents can learn successfully. It's a learning. It's a learning algorithm. Okay, it's a learning algorithm. So how it can learn successful control policy by experimenting in this environment. That is the objective. Okay, so and the goals of an agent. Goals of an agent. What usual goal we are taking? We have to maximize the cumulative reward, right? On each transition, you will be getting the reward, and on that cumulation of all those rewards, maximum value of that I mean, the policy that is giving the maximum value of all the cumulative rewards can be the objective. Okay, so the goals of an agent can be defined by reward function. What this reward function will do? Reward function will assign a numeric value for a state action pair. Okay, there will be a state action pair will be there, and this reward function will be assigning a numeric value for that, like 100 or 0, like that, minus 100, like that. So each distinct action the agent may take from each distinct state. Okay, na? So when the agent is in one state, it can take many out of many possible actions. It can take one action, and there will be some reward function which is defining the reward value for that particular action. Okay, so the goals can be defined in terms of reward function and also the actions that will be taken by the agent. Okay, so the same example, goal of docking to the battery charger. This has to happen when the charging is low. Okay, so a positive reward, that is example plus 100, when it reaches to that state, that a positive reward of 100 is given, and a rest all states a 0 reward will be given. Okay, so a positive reward of plus 100 to state action transition that immediately result in the connection to the charger immediately. Okay, so that then it will be given as 100, and a reward of 0 to every other state action transition. Okay, na? So so these are the example for the goals. Okay, goals and the reward function. Okay, next. See the reward function. See, this reward function can be built into the robo, and it may not be known to the robo also. It will be known only to the external teacher who provides the reward value for each action performed by the robo. Okay, so this reward function may not be known to the robo also. Next, the task of robo is to perform sequences of actions. Okay, observe their consequences in the sense rewards. Okay, and learn a control policy. Okay, this is the objective. Learn a control policy that will maximizes its cumulative reward value. Okay, or in the sense it will achieve the goal. Okay, the robo has to achieve its goal. And then the control policy we desire is one that from any initial state, it can be in any state. There may be a set of states possible. Out of that, it can be in any state. Chooses action that maximize the reward accumulated over time by the agent. Okay, so the action that has to maximize the reward, that action has to be chosen. Okay, so we will see this gamma value. Okay, see here we have this gamma also, right? So this gamma is called as the discounting factor. Okay, gamma is called as the discounting factor. See, there is a we are getting R naught. R naught is the reward, right? When we are getting R naught from moving from state S naught and taking action A naught. When the agent is in state S naught, on taking action A naught, the reward is R naught, right? So and when we are getting reward R1, when the agent is on state S1 and it has taken the action A1, then we are getting the reward R1. So here gamma is called as the discounting factor. See, why? Because gamma value is between 0 and 1. Okay, now between 0 and 1. Thing is that, see, when you are getting delayed rewards, okay, when we are getting delayed rewards, in the sense when we will get a reward R1, when we are in a state S0, let us say we are in the agent is in the state S0. Let us say agent is now in the state S0, and when it will get a reward R0, after some time, what is that time? It has to make an action from S0 to A0. It has to make that action A0, and on that action it will reach state S1, and from S1 it has to make an action A1, right? And then only it will get reward R1. Okay, when R0 is R0 reward, it got this R0 reward earlier, and when did this get this reward R1? Lately, right? R2 even more late. Okay, now we are assuming that the agent is in the state S0, initial state is S0. If that is the case, then we got R0 much before, R1 we got it lately, and R2 we got even more later. So see here, when the we have seen this example, right? It has to see, this example is there, right? So when the charging is low, then what it has to do? Immediately, it is saying immediately it has to dock itself to the battery charger, right? So what happens if it delays? If it delays, then the value of that reward also degrades. Okay, so that's why we have this discount factor. This value of the reward degrades by gamma. Okay, and the value of the reward R2 degrades by a factor of gamma square, and this is between 0 and 1. This is between 0 and 1. And let us say we have the gamma value. Let us say we have taken the gamma value of 0. Then all these rewards, R1, R2, all are made to 0. Only we will get a final reward of R0, right? In that case, if it is more important, if the time is more important, okay, now if the time is more important, then time in the sense, I mean the number of transitions, okay, if that is important, and then in that case, what we have to move gamma value near to 0, okay, na? Near to 0. If there is no such limit, our objective is to go to achieve that goal. That's it. In that case, gamma can be 1. All rewards can be given a value, equal value. Okay, if you want all rewards to be given equal value, if you don't want to decay the value of the reward, okay, then in that case, we can give the gamma value as 1. Then what will be this value? R0 plus R1 plus R2 plus and so on, right? So, so this gamma accounts for the discounting factor. Okay, gamma is a discounting factor. Okay, so learning we will see that also in the later slides. Okay, so learning a control policy. So what is the objective is to learn the control policy or the control strategy, or it can be said as sequence of actions. It is like maximizing this cumulative reward. What is this reward? This is the cumulative. So plus, okay, all rewards. This, with a discounting factor, we have to maximize this value. Okay. So learn.
Excuse me, ma'am. I have one question.
Yeah.
Can you please give one example where gamma value, that means a specific example where gamma value will be near to 0 and where that is not.
Yeah. So example is like see. Yeah. So we will once again take the same example. This docking to the battery charger. Okay, na? Docking to the battery charger. That is our goal. Goal of the agent is docking to the battery charger when its charging is very low. Okay, na? That is the goal. And then see, the reward it will be getting is 100, right? When, I mean, final state. Okay, a positive reward to state action transition that immediately result in the connection to a charger is 100. But see what happens. Let us say some SC8 or something is SC8. Let us say S8. S8 is the docking state. Okay, na? Let us say S8 is the docking state. And now the agent is at S0. Okay, na? Now the agent is at S0. So to go to that state, what it has to do? If we could see, there is only one action. Let us say if there can be many actions also, right? There can be many actions also. Okay. And the docking state is S8. Now we are at S0. Agent is at S0. Then what it has to do? It has to take action A0 if it will reach S8 only following the sequence of actions, right? So it has to take action A0, after that action A1, and then A2, like that, and finally it will reach to state S8. Consider the case, consider another case, okay, where we have multiple actions. Okay, so yeah, so see here. Okay, let us say there are multiple options are there. Let us say the agent is at this point, and it has to go to this state. Okay, see here, when it goes follows this path, or it can follow this path and finally go here, right? So there are multiple paths are there for the agent to reach to the final goal. Okay, so what happens? What happens when the it's delaying, it's making more and more transitions. This is the case where it is making more and more transitions. Okay, more and more transitions, but time is elapsing, right? In the meantime, time is elapsing, isn't it? So even though you will get a reward, that reward will be depreciated. Okay, here time is important, otherwise it will become dead, right? If it is not charged, or if it is not docked, it's what to say, it will be switched off, isn't it? After some time it will definitely switch off, right? So the time is important here. That's why we are having this discount factor also. Okay, even though you get a reward also, the reward getting the reward after a long time is of no use. That's the sense here. Okay, na? Is this clear? You are getting the reward, but after once this what to say, I mean, getting the reward after a long time. Okay, so that doesn't make any sense. Okay, so getting a small reward, but that is within the time. Within the time will be of more value, weightage. Okay, so did this answer your question? Okay, that's why we are adding.
Yeah, ma'am. Thank you. Thank you so much.
Discounting factor. Okay, discounting factor. I mean, getting reward at first second is not the same as getting 100 after 1 minute. Okay, that is the point here. Okay, let me. Yeah, so this is, yeah, we are in this slide. Learning a control policy. Okay, so that is objective is to learn a control policy, and here we have to maximize the cumulative reward. Okay, so learning to control sequential processes. Okay, so control sequential processes in the sense sequential actions. Okay, so we have to learn that. Okay, and applications are we have already seen these things: manufacturing optimization problems and sequential scheduling problems. See, taxis to send for passengers in a large city. See, the optimization here is the car driver or the cab should not be free for more time. Okay, the cab should get more and more order. What to say? More and more pickups and all. Okay, so that is the maximization we have to do. And what else? Minimization of petrol consumption. Okay, at the cost of minimum petrol consumption. So such problems can be solved using reinforcement learning. Okay, so Q stands for quality. So here quality of a sequence of actions. When we will say that this quality, the actions are of good quality when they are ending up in a maximum cumulative reward, then we will call that sequence of actions as more of or having more quality. Okay, so we'll see it. Cumulative reward function is used to define the quality of a given action sequence. Okay, so we are using this function. And then see here, there are certain things like deterministic or non-deterministic outcomes. when you see the first example, that is deterministic. Okay, na? Why deterministic? Only one action is there from S naught. S naught, only one action is there, A naught. That is called deterministic. And when we see the other example, we can move up, down, left, right, and all, right? And we can rotate by, I mean, we can do a that is an example of non-deterministic. Okay, so there will be these settings should also be there, whether we are with a deterministic or non-deterministic problems. And then the agent has or does not have prior knowledge. What is this prior knowledge? Prior knowledge is the agent knowing whether what are the transitions. See, on a state, the agent should know these transition functions, transition output of the transition functions, like when it is moving, when it is making an action A naught, when it is in state S naught, what is the state it is ending up? Okay, so S1, that is the state, right? Whether that information and R naught is the reward that it is getting. Okay, S naught and R naught. Okay, so whether this agent knows this information or not, whether it is aware that it will be ending up in S naught or with a reward of R naught or not, that is the prior knowledge. Okay, transition functions are defined or the reward functions are defined. So that is a prior knowledge. Okay, let me go to that. Okay, so whether the agent has or does not have that prior knowledge, that is also another setting about the effect of its action on an environment. So, and then TD, see, 1995 TD Gammon program, it's an example of reinforcement learning, and it has become a world-class backgammon player. Okay, and it has won some competitions also, tournaments also in with the top ranked players. Okay, so it has been trained on 1.5 million self-generated games. 1.5 million games it has been trained, and it is almost equal to the human players. Okay, and it has won many tournaments with the top players. So that is an example, best example of reinforcement learning. And target function in the sense objective. Okay, what is the objective here? Objective is to learn the control policy, right? And what is the control policy? Control policy is the sequence of actions. Okay, control policy is represented by pi. Okay, so it is a sequence of action on state, which action has to be taken. Okay, and this is the policy. Let us say 6 states are there. 6 states are there. Okay, na? 6 states are there. Then S naught, which action I have to take, agent has to take. Okay, so that objective is the cumulative reward will be maximized. That is the objective. And then this pi will have S naught comma some action, S1 comma action, like that for all the 6 states. For all the 6 states, an action will be defined. Okay, so the target function is a control policy. This is the target function. This has to be learned, and that outputs an appropriate action A from a set capital A. Okay, so there is a is the set of all actions, and S is the set of all states. Okay, given the S. Okay, so it maps from the current state S action A equal to pi of S. Okay, so this is mapping. Pi is a mapping function from S to A. What is that mapping? Mapping is a optimal action. Optimal action. It has to take. All this optimal action in turn leads to optimal policy. Optimal policy, and optimal policy will lead to maximum reward. Okay, so and then we have how reinforcement learning is different from other approximation task. How it is different? Okay, so delayed reward is one thing, and exploration, partial observable states, lifelong learning. These are all the factors by which reinforcement learning is different from other functions. We will see one by one. Okay, so delayed reward in the sense we have already seen that, right? delayed reward. Okay, so we will not be getting all the rewards at a time. Okay, so see here, what is this? Pi is a policy, right? Pi is a policy, that is the transition function. Okay, pi of s means some action, right? So what it will do, it will give some reward, isn't it? Okay, it will be giving some reward. Okay, so a delayed reward, in the sense, availability is a sequence of immediate reward values as the agent executes its sequence of actions. Okay, on performing this thing, it will get a reward, and on performing the next action, it will get another reward. Okay, so like that, it will be getting rewards on each transition of the state. By taking one action, it will get some reward. Okay, so and the exploration is exploitation and exploration. The reinforcement learning, in reinforcement learning, we have a trade-off between exploration of unknown states and actions. Okay, so it has to explore all the states and all the actions also. It has to learn, it has to explore, in the sense, see, let us go back to the example. There are so 6 states in our example, right? 6 states are there in our example. What it has to do is, what the agent has to do is, see, on state yes, let us say this is state S1, how many actions are there? 1 or 2. So it has to explore all these actions, and when it is in state, 3 actions are there, 1, 2, 3. While learning, I mean, in the Q learning algorithm, it has to explore all the states, all the possible states, and on that state, all the possible actions. Okay, and then exploitation is only a few states. It will be considering only few states where it will be considering states and actions that it has already learned. That is the exploitation. I mean, refining the Q values. We will see the Q values, V values, and all. Okay, the upcoming slides, we will see all those things. So it is refining the Q values of already seen states on the particular actions. Okay, exploration is it's visiting the new states on new actions. Okay, so partially observable states in the sense, for the same example, robo example, it might be having a camera, right? Front camera. If it is having only forward pointing camera, so it cannot, it can only sense the states that are forward, right? But it cannot sense the states that are at the back of the robo, right? If it has only forward pointing camera. Okay, so it cannot see what is behind it. So in order to do that also, see what we have to do. When we see at that state, it cannot view the states which are behind it. So we have to consider those states which are already behind, and then we have to explore those states. Okay, so let us see this. Consider its previous observations together with its current sensor data when choosing actions. Okay, previous observations together with it current sensor data. So both has to be considered. Okay, the previous observation, in the sense, when it is in the previous state, what are the states that it could sense, those things, and right now it is in some particular state, right? At that point, what are the states that it could sense? So consider both the observations. Okay, best policy may be one that chooses actions specifically to improve the observability of the environment. Okay, observability of the environment, in the sense, states, the states. Okay, what all states it can move from a particular state. Okay, that is the observability of a environment. So partially observable state, it has to deal with that situations also. Reinforcement learning. Okay, here we have an assumption like agent sensors can perceive the entire state of the environment at each time step. Okay, entire states of the environment. So when it is in a particular state, it can sense all the states that it can reach. Okay, that is the assumption that we are making, but in practically it may not be the case. Okay, only few states might be visible, sensed by the agent. Okay, so lifelong learning. It will be in an infinite loop. This learning will be an infinite loop. Okay, when you see the algorithm, you can see that infinite loop. So it has this mobile robot may need to learn see how to dock into a battery charger and how to navigate through narrow corridors. Okay, that is another goal. And how to pick up output from laser printers. This is another goal. And the goals list may continue, may grow, isn't it? So that's why it is called lifelong learning. Okay, na? The capabilities or the goals of the robot may keep on increasing. Okay, once it learns to do this, collect these printouts from the printers, later we may expect that to do some other task. Okay, so that's why it is lifelong learning. And robo learning often requires that the robo learns several related tasks. Okay, several related tasks within the same environment. It can be in a restaurant or it can be in an office, anywhere. Within that environment, there will be so many tasks that needs to be automated, right? So that's why it is called as a lifelong learning. Okay, using the same sensors also. Same sensors. Sensors can be cameras, sonars and all. Okay, so next the learning task. Okay, so what is the task that has to be learned? Okay, so the task is to learn the control policy. Okay, task is to learn the control policy. So the control policy is the sequential control strategies. Okay, sequential control strategies we have to learn. Okay, so we have an assumption. Okay, here we are assuming agent actions are deterministic or that they are non-deterministic. We already know that, right? When we have only a single action, a single state, when it is moving to a single state on a particular action, then we call deterministic, and non-deterministic multiple states. Okay, it will be moving to multiple states. Okay, so that also we have to see. And can predict, the agent can predict the next state. That is a prior knowledge. We are saying that as a prior knowledge, right? Prior knowledge in the sense transition functions. Okay, transition function. It will be represented by delta. We will see that also. So what is the state? Whether the agent knows whether the agent has that knowledge or not. What is the next state when it makes, it is going to end up when it is going to make an action A naught, something like that. Okay, and then what is the reward? Okay, so those things, whether the agent knows that or not, and then depending on all these things, the algorithm changes. Okay, we will see first we will see deterministic, after that we will see non-deterministic and all. Okay, so the agent is trained by an expert who shows its examples of optimal action sequences, or that it must train itself. So usually it will train itself by performing actions of its own choice. Okay, so between these options also the agent has to choose. Okay, learning algorithm has to choose. Okay, whether it will train itself or whether there is some training will be given some an expert in the sense trained examples. What are the train examples? Policies itself are the train examples. Okay, so policy, what is a policy? On state yes, what is the optimal action? Optimal action it has to take, and state S0 it has taken some action X, and state S1 it has taken action Y, and what is the goal? Goal is the decision there. Okay, so if that is given to the if those details are given, then it is called trained agent is called to be trained by the expert. Otherwise agent is getting trained by itself. Okay, so next is general formulation of the problem based on Markov decision process. Okay, Markov decision process is also the same, right? There will be transition states will be there, actions will be there, and on taking some actions, there will be a transition to the next states. Okay, so this is all deterministic. Markov decision process is deterministic. Okay, the agent can perceive a set S of distinct states of its environment and has a set A of action that it can perform. Okay, we have a set S this, and A is the actions. Okay, as usual. At each discrete time step R. Okay, so the agent senses the current state ST. Okay, chooses a current action AT and performs it. It is at a state ST, and now it is taking an action AT, and it will does that action AT, and it will get some reward RT. Okay, na? This is the reward that it has got. Okay, and it is ending. This is the R function, and this is the delta function. Okay, delta function is the transition function. Okay, na? And then it might be ending up in the state ST plus 1, right? And it will be getting a reward of RT on moving from state ST to state ST plus 1. It will be getting a reward of RT, and AT is the action taken. Okay, these are all the representations, and the functions delta and R are part of the environment and are not necessarily known to the agent. Okay, agent might not be knowing that information. Okay, assumptions we have already seen that, right? Prior knowledge or without prior knowledge, and is it trained by a teacher or self-training, and then deterministic or non-deterministic. With that prior knowledge, R function and delta function comes. Okay, so in an MDP, the functions, okay, delta function, transition function, and the reward function depend only on the current state and action. Okay, na? This depends upon only the current state and action. Okay, and not on earlier states or actions. Okay, we don't have anything like a S of t minus 1, A of t minus 1 with these things, right? On this current state, on taking action AT, what is the state it is ending up? We don't have a prior, prior states dependency or prior action dependency for this thing. These are all independent of the earlier things that has happened.
स्क्रीन दिख रहा है रिकेश? नहीं दिख रहा है, क्या बात कर रहे हो? ओके, मैंने लास्ट क्लास में आप लोग को यहाँ पे साइक्रोमेट्रिक चार्ट के न्यूमेरिकल करवाए. ओके, देखिए.
This is a transition function and this is the reward function, right? So here learn a policy. What is this? It's a pi is the mapping function from S to A, right? So from S to A, the task of the agent is to learn this policy pi. Okay, na? We have to, let us say 6 states are there. For all the 6 states, the optimal action has to be defined. Action that has to be taken has to be defined. Okay, so pi is defined as a mapping function from S to A. Okay, and for selecting its next action AT based on the current observed state ST, that is pi of ST equal to A. For all states we have to determine. Okay, greatest possible cumulative reward. Okay, that we have to maximize it, right? So assumptions here are in MDP, Markov decision process. Assumptions, what we are saying is S set and A set are finite. Okay, na? S set is the number of states. Environment is finite. Okay, or the environment can be infinite also, and they are all deterministic functions. There will be only a single state that it will be ending up on a particular action. Okay, and then A also. So these are the assumptions that we are making in the case of MDP, in the sense deterministic case. Okay, so cumulative reward value. So computing this cumulative reward value, that is represented by V. Okay, na? This is represented by V. And what is pi? Pi is the optimal policy, and ST is the state, current state, ST. Okay, current state. So this is the cumulative reward, okay, representation for that. Okay, the cumulative reward, this thing achieved by following an arbitrary policy pi from an arbitrary initial state S. St is the initial state. Okay, from we are starting at St, and this is all the cumulative reward value. So what it has got? RT. RT is the reward when it is in state St and it has took an action. Then it has got RT reward. Okay, first reward that it has got. And after moving to St plus 1 state, okay, and right now it is in the second state, and at that point when it is moving to the third state, it will get the reward RT plus 1. So, and this is the gamma is a decay discounting factor, and summing up all these values. Why it is dot dot dot? Because it is infinite. Okay, in an infinite environment. So that's why we are representing dot dot dot. And the summation of all these things can be the same thing can be represented like this with a sigma value and all. So this is the V of pi St. What is St? St is the start state. Start state, and we have to find the pi value such that it will be maximizing this cumulative reward value. Okay, that is the objective. We have to, among all the pi's possible, select the one, optimal one, that is having the greatest cumulative V value. Okay, na? Cumulative reward value. That is this value. Okay. So AT equal to some pi of St with reward RT. So this is all clear, right? AT plus 1 equal to pi of St plus 1 with reward this thing. And this is the discounted. Why discounted? Because we have got the gamma factor. That's why we are seeing it as discounted cumulative reward achieved by policy pi from initial state St. I am missing a T here, but it is the initial state is St. Okay, na? So this we have to maximize V value. Okay, na? Maximize V value. So this gamma we already know, right? Zeta will be between 0 and 1. It can be 0 and 1. It's a constant value. And then here we are saying that when it is at I step, it will be discounted by a factor of gamma power of I. It is still reducing. That reward value is still reducing as and when we are making transitions. Okay. In many cases, we prefer to obtain the reward sooner rather than later. That is the reason here. And if gamma equal to 0, only the immediate reward is considered. Next reward, immediate reward in the sense next reward. If gamma closer to 1, further rewards are given greater emphasis in the sense gamma equal to 1, then we will have all these values, right? Okay, there may be applications where gamma has to be 1, and there may be other application where gamma has to be 0. Okay, immediate reward, only immediate reward, that is the RT, that only we have to maximize. Okay, so discounting factor, this is about the discounting factor gamma. And then see other definitions of total reward. In addition to this cumulative reward, that definition we have that, right? This thing in addition to maximizing this value, this is the evaluation function. This is the evaluation function by which the pi is evaluated. Okay, na? Pi. This pi is the optimal policy. That policy is evaluated by this evaluation function V. In addition to all these evaluation functions, we also have other definitions like finite horizon reward. Finite horizon reward. That is, we are limiting it, and there is undiscounted. There is no gamma here. That is why it is undiscounted. Okay, na? So this is another type of evaluation function, and average reward is another type of evaluation function. Okay, see here. And H steps, here they are considering only finite, over a finite number of H of steps. Here we are taking infinite number of steps, right? Here it is limited to H number of steps. Okay, and it is undiscounted. That is a finite horizon reward. And average reward. What is this average reward? Here it is H is tending to infinity. Once again it is infinity, but it is undiscounted, and 1 by H. It is the average, right? So 1 by H of this summation. Okay. If you have any questions, please raise your voice. Okay. So we have, in addition to those V definition, we have other definitions also. Okay. And in the here in this context, we will be seeing only the V, but you can consider those other evaluation functions as well. Okay. Now we will be coming to the optimal policy. Okay. So the agent, what it has to do, it has to learn the policy by that is maximizing this thing, right? What is S? S is the initial state. Initial state. We have among all the pi's possible. What is pi actually? Pi is the function, mapping function from state to action, right? State to action. Among all these things, we have to choose the pi that is giving the maximum value for this thing. For all states, S. Okay. So optimal policy is optimal policy. That optimal policy, there are so many things possible, right? So many pi's possible, and optimal one we are representing it with a star. Okay, pi star. Okay, so it is like among all the pi's, among all the policies that are available, we have to select the one that is maximizing this value, and for all the initial states, okay, that pi has to win for all the states. Okay, so that pi we have to choose, and this is going to be a learning function. It will learn this V. Okay, na? That learn with this V. Value function. This V is called the value function. We once again see the Q function also. Yeah, we as of now we'll talk about this value function. Value function of the optimal policy. So optimal policy, when we are saying optimal policy, it is represented by star, right? So this is simply represented as, instead of all these things, we are representing that with this thing, V star of S. Okay, so this is the one that is maximizing the V value. Okay, value function. Okay, this is all grid. So if you see, these are the rewards. These are the rewards, and these are the V's. Okay, na? V's. What are these V's? Optimal V's. Okay, na? Optimal V's. Optimal V's in the sense, we have come up with a policy. We have come up with a policy, and we have learnt on a transit. Let us say we are in the state S1. Okay, we are in the state S1. And when we are moving from S1 to state S2, let us say this is the state and we have taken the action right. Then 81 is the reward that we are going to get. Okay, and from here, this is the learning. After learning, we got these values. First, we will see the learning algorithm. Okay, na? After learning, we got this algorithm. But let us go to the learning algorithm. Okay. The 6 grid squares, here he is talking about the single grid world environment problem example. Okay, world environment example, the 6 grid squares. Okay, 6 possible states are there. 6 possible states are locations. They can be called as locations also for the agent. And arrow is the action. So that's and all we already know this thing. Let me skip the slide. And goal state also we know, G, right? G is the goal state, and this is also called as the absorbing state. Why? In the sense, because it is the final state. From here there is no it won't move because self loop is there, right? On any action it will be still in its state G, so it is called as an absorbing state. Next is determining the optimal policy. Okay, here they have taken gamma value as 0.9. Okay, na? One optimal policy is the figure. Okay, bottom figure. Okay, this one. Okay, this is the optimal policy. We will come for that. Okay, how we got this optimal policy, we will see. So, but as of now, this is the optimal policy. Like when it is in the state, then it has to take the right action. And when it is in the state, when it is in this state, then also it has to take right action. Okay, na? Right, move right. And here also move right. And when it is in this state, move right. Among all these possible, many actions are possible, right? And these are the only actions that are there in the optimal policy. Okay, so Each arrow can take a move from one state to another, and yeah, this is already done, right? So the optimal policy directs the agent along the shortest path. This is definitely the shortest path towards the goal state G. Okay, this policy specifies exactly one action. Okay, na one action. But earlier multiple actions are there on each state, but finally optimal only one action that the agent will select in any given state. Okay, na? So this is about determining the policy, optimal policy. And value function V. See the value function V. Okay, the value of V star for bottom right is 100. Okay, so here, 1 second. Yeah, this is the V star for bottom right. This is 100. And here it is V star value of the state S2. Let us say this is S2. That is 90. And here it has 81. So these are all the V star values of the states. This is the values that we have to get after learning. Okay, na? So, yeah, let us see this. So value of V star for bottom right is 100, because the optimal policy in this state, see, on making a move up, then it will go to the final goal state, right? That's why its V star value has come to 100. And here also V star value has come to 100. What are the actions that it can take? It can move to right or it can move to left also. Okay, and here it is the V star value is 90. But this optimal policy or this optimal values are one among the many possible values. But we cannot say that there exists only one optimal solution. Okay, na? There can be many. Okay, so see here the value of V star for the bottom center is 90. So because why it is 90? Because it has to make one more move, isn't it? One more move to the next state, and 2 moves it has to make. That's why it has come to 90. And the discounted future reward, you already know, right? When we substitute 0.9 in that example, then you will get this is the reward. All state has got a reward of 0, isn't it? All state has got a reward of 0. See, what is V value? V value is V value. Formula is there, right? V value of this equal to RT. Okay, plus gamma of RT plus 1. When it is in the this state, let me go there. When it is in this, when it is in this state, I mean this state, okay, this 100, right? So it will be 0.9, because gamma is 0.9 into that 100 reward we will be getting, right, into that 100 plus 0. 0 is the reward that it is initially. So this 90 value is computed for this state. Okay, this state, the reward computation for this state. Okay, I mean the V value for this state. Okay, that is equal to the reward from this state, and on moving to this state, reward is 0. Reward is 0 plus gamma times. Gamma is 0.9 into the reward on moving from this state to this state. That is 100. 100 is the reward, right? So 0.9 into 100. So it will be 90. Okay. So we will see the algorithm. Okay. Yeah. Q learning. Q learning is the algorithm. First we will see the introduction of it. After that we will see the algorithm part, evaluation function, Q function. After that we will see this algorithm to learn. This is the algorithm, Q learning algorithm to learn the V values. Actually it is learning the Q values. We will see how you got, we have ended up in Q also. Okay, so yeah, after learning, that example, those values are after learning, that all that scenario is after learning. Okay, after executing this algorithm and all. Okay, and then we will start with the Q learning. Okay, how can an agent learn an optimal policy 5-star for an arbitrary environment? That is the question, right? How to learn this? Okay, so that we will be dealing in Q learning. Okay, training information available to the learner. What is the training information available to the learner? Here, this is the assumption. R of Si comma AI. What is this R of Si comma AI? Reward. We are assuming that this information is available to the learner. Okay, immediate rewards. Okay, this information is available with the learner. And then see here. Yeah, optimal action from state yes. Okay, what is the optimal action we have to take from state yes? What is this V star? V star is the value of the state. We are at right now we are at a state yes. Okay, na? We are now at a state yes, and we have on the action, on some action A, we have moved to some state some S prime. Let us say S prime. Okay, we have moved to the state S prime. So V star of S prime is the value function, and then here we have got gamma, right? The discounting factor, and the reward. This is the reward of S comma A. On making this transition, what is the reward that we have got? Okay, na? And then the optimal policy from state yes. This is the state yes. That is the one which will be giving this maximum value. Okay, na? The action that is giving this maximum value, that action will be considered as an optimal action from state yes. Okay. Okay, na? So the optimal action in state yes is okay. So this is all the thing that maximizes the sum of the immediate reward. This is the immediate reward, and then the gamma, and then the gamma times the value for V value. Okay, V value of the immediate successor state discounted by gamma. So whichever action is giving this maximum value, that is considered as an optimal action that has to be taken when the agent is in state yes. So by this we mean that. Okay. Thus, the agent can acquire the optimal policy by learning V star. Okay, by learning V star value, provided it has perfect knowledge of what. So this already knows this value. What the reward function it knows, transition function it also it knows. Okay, when it knows this transition function and the reward function, then getting this thing is learning the V star value. Okay, same as the learning the V star value. So now we have to learn the V star. Okay, so how we have to learn, we'll see. The agent should prefer state S1 over state S2. Okay, whenever these values are more, okay, whichever value has got the highest value, that state has to be chosen. Okay, na? So the agent should prefer state S1 over state S2. Okay, whenever this condition holds, so whichever is having the maximum V value, okay, that state has to be chosen, because the cumulative feature reward will be greater from S1. Okay, so next assumption is that so here also we are assuming that delta and R are known, because here we have got delta and R. So that is the assumption. And next we are having the evaluation function Q. Okay, we are introducing the evaluation function Q. Okay, so in many practical, see here when we are talking about the V function, we should know the prior knowledge. Prior knowledge should be given to the agent. That is the delta, transition function delta, and the reward function R. That has to be known to the agent. But what if we don't know that information? Then we will be going with the evaluation function Q. Okay, in that case we will be going with the evaluation function Q. Okay, in many practical problems such as robo control, it is impossible for the agent or its human programmer to predict in advance. So that transition function will not be known, and the reward function will also be not known. In such cases, we will be going for the another evaluation function Q. Okay, more general settings in the sense we don't know the delta function and the reward function. Okay, next is the Q function. Now see the Q function. Q function is the reward received immediately upon executing action A from state S plus the value of discounted by gamma of following the optimal policy thereafter. Okay, so Q value is given as like this. Okay, so it is a reward plus this V value times the V value discounted by the gamma factor. Okay, so Q function is defined this way. Okay, Q function is defined this way, and then we can change the optimal function. Optimal function pi is there, right? Pi is there. Pi, it is having values in V's, right? It is having in a V function. So now we will change it to Q function. Okay, note that this is exactly the quantity that is maximized. Okay, so here we are replacing the policy, optimal policy for when the agent is in state yes. Optimal policy in the sense which action it has to take. So it has to take the action that is giving the maximum this value, right? So this is the Q function. Okay, na? We are rewriting. Simply we are rewriting the V function in terms of Q function. Okay, na? Okay, so the pi, I mean the optimal policy for state yes, that can be written in terms of Q like this. Okay, the maximum action that is generating the maximum Q value, that is given as the action for optimal action for state when the agent is in the state yes. Okay, so we are rewriting. Next, why is this rewrite important? Why we are rewriting is, here we don't know, we are assuming that delta and R are not known. So no knowledge of the functions. If you see here, no knowledge of the functions. That's why we came up, we have rewritten the this thing pi in terms of Q. Okay, now you have to learn Q. Okay, that's why it is Q learning algorithm. It need only consider each available action A in its current state S and choose the action that maximizes. We have to choose the one that is maximizing this. Okay, so if you take that Q value, so now the algorithm is about Q learning. Okay, we will see the algorithm. Okay, so if we go back to this simple grid example, we will be seeing the Q values. Q values are the one among all the possible V values, it will be selecting the one that is having the maximum V value, the action that is having the maximum V value. Okay, Q value for each state transition equals the R value for the transition plus the V star value for the resulting state, discounted by this. Okay, so next is an algorithm for learning Q. Okay, we will see this algorithm and we'll end this session. Okay, so learning the Q function corresponds to learning the optimal policy. Okay, na? Q function, it's a learning Q in the sense pi is written in terms of Q, right? Now we are learning Q, then it means that we are learning pi itself. So the key problem is finding a reliable way to estimate training values for Q. Okay, given only a sequence of immediate rewards are spread out over time. Okay, relationship between Q and V star, we already know, right? V star of S is max of A, the action A that is giving the maximum Q value. That is the relationship between these two things. So the same Q of S comma A, it can be V star is the maximum with this thing. With this thing, we can replace that here. Here, and we can write Q of S comma A as R of S comma A plus gamma of max of A. That is the maximum action, the action that is generating this maximum value. Okay, delta of S comma A dash. Okay, so now see, now what we have done, we have written Q in terms of Q. Now it has become a recursive definition. Okay, recursive definition. And next is in this algorithm, the learner represents his hypothesis. So here we are taking the Q prime, okay, learner's estimate of Q function. Okay, so if this Q is the actual value in the sense optimal values, the values that are leading to the optimal policy. And now we are doing an estimate. We are computing the estimate Q prime. Okay, na? Q prime. So what we have to do is initially there will be, we have to construct a table. Okay, construct a table in the sense what are the rows and what will be the columns. Let us take rows as the states and columns as actions. Okay, and for all the state action pair, we have to initialize the Q values. Okay, we have to initialize the Q values with some random values. Okay, and then from that random values, we have to update. We have to learn the Q values. Okay, we will see the algorithm training Q prime. Okay, so let us see this, and after that we will go back to the previous slide. Okay, so this is the Q learning algorithm. Okay, so what we have to do for each S comma A, for each pair. Okay, the table entry Q of estimate, this is the estimate value that is set to 0 for all possible combination of state action pairs. We made it to 0, and then observe the current. Now we have to see the current state. It can be the initial state, right? Initial state. Okay, initially it will be in the initial state. At this point it will be the initial state, and do forever. Okay, na? This is forever. Okay, so select an action A and execute it. Some action you select from state, yes, there will be some action, many actions, right? Out of that, those many actions, you select one action and you execute it. Then you will be receiving this immediate reward R, right? So you will be receiving the reward R, and observe the new state S prime. Okay, na? S prime. Okay, now you have got the new state S prime, and then update the table entry. So now what we have to do on making an action A, when the agent is at state S, the reward it has got plus the discount factor times the maximum value of the estimate on state S dash. What is S dash? S dash is the state that it has gone after performing the action A. Okay, na? After performing the action A, out of all those actions possible, we have to take the action that is maximizing this Q value, and then when it is multiplied with the discounting factor, along with we have to sum up this reward, immediate reward. R is the immediate reward, and the Q value entry, I mean this S comma A in the table will be updated accordingly. Okay, this is the learning. This is the learning that we have. We are doing here. We are learning the Q values. Okay, first we have written pi in terms of the V function. After that, we have written pi in terms of the Q function. Q function, because of no prior knowledge, there may be situations that delta and R will not be known. These functions will not be known. So we are considering the pi in terms of pi in the sense optimal policy in terms of Q values. So this is the learning that will happen, and it will be iterating in this loop, and then we have to see it has moved from S to S prime, right? So the state now has to change to S prime. Okay, once again iterate over this loop and update these values. Okay, so the leaf till the algorithm converge. Okay, so this is the Q learning algorithm. Okay, and then let us see these things. The agent repeatedly observes its current state S. Okay, chooses some action A, executes this action. Okay, now it is choosing some action, executed action, and then it receives the reward, and then it goes to the new state S prime. And then after that, what it is doing, it is updating this value. Okay, now this now after updating this value, we are making the state to S prime, right? So the same thing is told here. Okay, this is about Q learning. Assumptions of this algorithm are the agents estimate Q prime. Using this algorithm, agent is estimating the Q prime, and the assumptions are, now we are thinking that it is a deterministic. We have done it for a deterministic Markov decision process. Okay, converges in the limit to the actual Q function, provided the system can be modeled as a deterministic Markov decision process. The reward function is bounded. Bounded in the sense, reward cannot be infinite. Okay, so we are assuming that the reward value is something constant. Above that, we are assuming a threshold for the reward value. Okay, na? So all the rewards has to be within that threshold, whether it is positive or negative, all that has to be within that threshold. And then actions are chosen so that every state action pair is visited infinitely often. Okay, na? Infinitely often. So when we are choosing this action, we are selecting this action, right? When you select the same action again and again, then what happens? We will be updating, refining this entry only. Yes, comma, A, that action only we will be updating. So what we have to do? Each time you have to explore, that is explore, exploitation and exploring we have seen, right? In the first slides we have seen exploring and exploitation. When we are selecting the same state, same action, we are updating these Q values for the same S and A, then it is called exploring, exploitation. And when we are doing we are covering all the states with all the actions, then it is exploring. Okay, so assumptions are this thing, infinitely. Every state action pair is visited infinitely often, because we are in the infinite loop, right? So we are assuming that this is also done. Okay, and this is the example of the same grid. So see here, we are in the state S1. This is the state S1. And then the next state is, this is the state, and the action taken is right. So this is how we will be updating. Okay, na? Initially, what we will have all the initial values as 0 or some random values, right? Q values are all initialized with 0 or some random values. Okay, so after that, each time in the learning process, those values will be updated. Okay, na? During learning, all those values will be updated. So if we see here, when it is in the state S1 and we are taking the right action, then what is the reward? Reward is 0, right? Except for the goal, it is 100. Rest all are zeros. And what is gamma? 0.9 is the discounting factor. And maximum you have to take among all these things. Okay, so you are ending up in the state on taking action, right? We are ending up in the state among these things, all the maximum these values. Okay, so 100 we are getting, right? 66, 81, 100. Among all these actions, select the one that is giving the maximum Q value. So that is 100. How did you get? Initially they will be all random values, but while learning they all will be updated. So this will be maximum out of this is 100. So 0.9 into 100 is 90. So now we will be, so this is updated, right? 73. Earlier on S1 comma right, it is 73. Now S1 comma right is updated to 90. Like that we will be updating each Q value. Okay, na? So let me end this here. There are a few more things like the convergence, how this algorithm, whether this algorithm is going to converge or not, and then non-deterministic rewards and actions are there, and temporal difference learning is also there. Okay, so non-deterministic in the sense when we here and all we have assumed that we are working in a deterministic MDP, right? Let me just have a glance of all that. Okay, so yeah, so here there are probabilities. From one state, there is a chance of so many states on a given action. Okay, earlier we are assuming that on a particular action, on a particular state, there will be only one state. Now there are so many state possible on a particular action on a state. Yes, sir. Okay, now, so the probabilities, with some probabilities, it is going to state S1 and another probability it is going to state S2, like that. So we will be considering this probability factor also. Rest all are the same. Okay, now, rest all are the same in the Q value, except we have the probability values included. That is about non-deterministic rewards and actions. Okay, on actions we will be going to, on one action we will be going to so many states. And temporal difference learning is, see, we are considering only the next state, right? Earlier, the only difference here is we will be considering so many states. Okay, so like earlier we have considered only the immediate state, like ST to ST plus 1. Okay, now we are considering, we are learning this Q values in terms of ST plus 1, 2 more steps, and learning in terms of N steps is this thing. Okay, for N step, this is the Q value. Okay, these are something about this is the introduction part of reinforcement learning. And yeah, with this I will end today's session. If you have any questions, you can ask me. Yeah.
Ma'am, thank you for your wonderful session, ma'am.
Yeah, thank you. Any questions are there? Are you able?
Participants, if you have any questions, you can post it in chat box or you can unmute and ask.
Shall I end the session? If
I think there is no questions from participant side, ma'am.
okay, then.
We
Okay.
can end the session.
Yeah.
Thank you, Srilata ma'am, for joining here and delivering a talk on reinforcement learning. Thanks for your.
Thank you, madam. Thanks a lot. Okay, thank you all.